Okay, so we'll start with our quick look at the calendar. Shh. We're missing a few people, but it's 10:40, so we start. Hopefully people will trickle in. Today is the 23rd of March. Happy Friday. Today we start an important topic known as inverse trig functions. And again, the fact that there's 3 days, 3 classes spent on this one topic is my way of saying I think it's really important. Project number 6 is due today. We have a quiz coming up on Monday. Any questions on the calendar? All right, so given that the calendar is right here, let's also look at the next couple of days. So today and Monday and Wednesday, we're going to talk inverse trig functions. Friday, 1 week from today, is our review day. And then 1 week from Monday is our second test. It is not too early to start studying for our second test. A week from this coming Monday. In the packet, if you look around, you will find some sample test problems, just like you did for the first test. And just like you had available to you for the first test on YouTube, I have made videos of me going through all of the sample test problems for test number 2. You can see it down here towards the bottom. And so you can go in there and you'll see me working through every one of the sample test problems that you will find in the packet if you look hard enough. Also at the top, I've started making the ones for test number 3, and we'll get through. Okay, so one thing I wanted to do before we dive into the new stuff, this inverse trig stuff, is just take a look at one of the homework questions from last night, and it has to do with the graph of the tangent function. So I put you here just so you'd have the graph of the tangent function in front of you. I copied it onto the next page, just a smaller part of the graph you are looking at. And the problem over here, this was 25 and 26, said give possible formula for the function. Okay, so remember we had a change of edition from this textbook from the last time I taught it to this time, and I think I spent about 12 or 15 hours just looking at these homework problems, and I'm certain that I made mistakes assigning some questions when I shouldn't have. Here's one where I know I did not give you the tools to answer this question. It's another mistake, but let's fix it right now and give you the tools to graph this kind of a thing. So the first thing, it is definitely not a sine or a cosine, right? I mean, it doesn't look anything like sines and cosines. So we're thinking of the graph of tangent. We've got the untransformed graph of tangent on the left, and our job is to see if we can somehow move this guy left and right, up and down, smush it, stretch it in such a way to make it land on the graph in number 25. Okay, first thing I want to point out is that we need to know the period of tangent. And we wrote this down last time. Anybody remember or can find or can look up here and determine how long does it take for tangent to give you one complete cycle? It's just pi, which is a big difference from sine and cosine. What's the period for sine and cosine? It's 2 pi. So they're different. Tangent repeats twice as often. And so what that means is that, do you guys remember the formula we had for b? B was like this number sitting in front of the t. The formula for b was 2 pi over the period. You guys remember? We've used that a few times doing sine and cosine stuff. Well, it's not that formula for tangent. The 2 pi is up there because sine and cosine normally have a period of 2 pi. That's why it's 2 pi. But if you're doing the tangent function, what should be on the top? It should just be 1 pi. So for a tangent, the formula for b is pi over the period. Okay, so let's think about the period. Looking at this top graph right here, the question is how far is it between one vertical asymptote and the next? I can look at that. I see a negative pi over 2. I see a positive pi over 2. How far apart are they? They are pi apart. Is that the normal answer for tangent? Yes. So this graph has not been stretched or compressed horizontally. Thinking of this b formula, if you decided to use it, you would take pi always, divided by the period of the graph you're trying to build. What is the period of this graph? It's pi, and you find out that b is 1, which means you don't need to stick anything in front, All right, so that's that. Next thing to look at, let's do more horizontal stuff. The question is, has it been shifted left or right at all? Okay, normally, where's the first positive vertical asymptote for tangent? So normally the first positive vertical asymptote for tangent is at pi over 2. Where is the first vertical asymptote, positive one here? It's at pi over 2. Have we shifted left or right? Oh, we might have actually, but we don't need to, right? I mean, you could pick this whole thing up and move it over and land it and nobody would know the difference. All right, so there's no need to worry about shifting horizontally. So we've got all the horizontal stuff taken care of. Let's think about vertical stuff. Vertically, you could push the entire graph up or down if you wish. What is this is something that Garrett had talked about, the midline of tangent. Maybe it doesn't have any meaning, but if we're going to say there is some middle to the tangent, then you could make a case that the x-axis is the middle of the tangent graph, the midline. What's the middle of the graph in number 25? It sure looks like there's some kind of symmetry happening around the x-axis. So it feels like, has it been moved up or down at all? Doesn't seem like it, right? We haven't shifted anything up or down. So then the only other thing we might deal with is a vertical stretch or compression. And how are you supposed to know if it's been stretched or compressed? They all look exactly the same, right? Like 25 looks like 26, which looks like the graph on the left. Vertically, I mean, they just look the same. Okay, so here's definitely a tool that I did not arm you with last time. Tangent has a nice point that you should be aware of. The tangent of pi over 4, or tangent of 45 degrees, I think it's one of the ones we looked at last time. Tangent of 45 degrees is nice. Anybody know what it is? It's 1. It's one of the very few nice values of the tangent function. Tangent of pi over 4 is 1, and you see that on this graph right here. This point is at pi over 4, comma 1. That's the nice point. That's like your grounding point that you can reference. So then we come over here and we look, is there a nice point that they're giving us? And well, the answer is yeah. I mean, like they're saying something is about that 1/2. They're telling you this is a special number right here. It's only special if you recognize that they're telling you what happened to the old point, which used to be up at 1. It is now only at 1/2. So if I'm thinking of vertically stretching or compressing the original, which one do I need to do to get it to land on a 1/2? We need to compress it. We need to multiply it by 1/2. If you turn that 1 into a 1/2, you multiply the 1 by a 1/2. And so if you're vertically stretching or compressing, where does that number go in terms of the function? Like if you're writing the new function, how do you vertically stretch or compress? Yeah, the whole thing gets multiplied. So it used to be y equals tangent of t, but because we wanted to vertically compress this by a 1/2, we stick a 1/2 in the front. That's the equation for that graph. 1/2 tangent t. For all the sine and cosine graphs we've done, I keep harping about plotting 5 special points. It's different. We don't have 5 special points. I mean, at most we have 3. There's the one that's purple, there's the origin, and then there's the symmetrical one down here in the 3rd quadrant. So you can plot those 3 points, you can focus on those, but still you need to do more work. You need to do different work to graph tangent than to graph sine and cosine. I think it's much more important to me that you can graph sine and cosine really well. I'm not so focused on graphing tangent really well, but anyway, since I assigned it and I didn't give you all the stuff you needed, I just wanted to mention that here at the start. Any questions on that one? Okay. So let's go to the next page. 26, sure. Same kind of idea in fast forward for the parts that aren't important. You can check that the period of this is pi. It has been unaffected. The midline is still the x-axis, so there's no vertical shifts happening. The reference point is normally up there at 1. Where is it here? It's still at 1. I mean, we haven't stretched or compressed like we did before. The only thing that's changed is what? We've got some moving over, left and or right kind of thing. So we just have to figure out how far to move. Normally the asymptote, the first positive one, is at pi over 2. Now the first positive one is at 3 pi over 4. Kind of have to be good with your fractions to figure out which one is even bigger than the other one, but which one's bigger? 3 pi over 4 is bigger. How much bigger is it than the pi over 2? Yeah, if you do 3 pi over 4 and subtract the pi over 2, you'll find out how much you have moved. You have moved pi over 4 to the right. So the last piece here is to write the equation I know that left-right movements are inside those parentheses. How do you move to the right? Subtract. So I think that that's an equation of the graph. Thank you.
Question, but can you just easily look at that as a bigger shift?
Absolutely. You bet. How far did we shift to the left? What you're saying, shift left?
Yeah.
Okay, so for example, how can we shift to the left? So maybe this pi over 2 didn't get shoved over to the 3 pi over 4. Maybe the pi over 2 went to this guy. It actually went left. So the same idea as before, we got to figure out how far we have moved. Pi over 2, so when we wanted to get on negative pi over 4, we subtract pi over 2. What do we get here? Is that 3 pi over 4? Positive or negative doesn't matter to me. I mean, like, they are 3 pi over 4 apart. And Garrett is saying we have gone left. So what's another version of this equation? Y equals tangent of t for Topher plus 3 pi over 4. And if you graph both of them, you'll see they land exactly on the same spot.
And you could have it even be a bigger shift.
Mm-hmm.
So it's really
Makes grading very challenging. Yeah, there are infinitely many answers to this question. Same thing was true for sine and cosine. Infinitely many things will land on the same sine or cosine graph. Good. Okay. So inverse trig stuff. This is my third time teaching pre-calc here at GCC. And so this is my third time working through this section. And every semester I change the material, these packets, I update them and try to make them better. And one of the sections that has always been problematic for me, I say always, the 2 times that I've done it before, has been this one. And so this one has undergone some more revamping than, say, the average section that we go through together. And I thought it was pretty good when I, kind of put this to rest in January. But I've been looking at it over the last 12 hours, and I have made some more changes. But of course, you don't have these changes. So we're going to go kind of, I'm calling it audible today. We're gonna change a little bit from the plan that you guys have in front of you. I have a new plan. It's on these 2 pieces of scrap paper. I will share it with you. But there's going to be a little bit more copying today, just because you don't have this stuff. I don't have a nice version of this. So we're going to do some things that are in here and some things that you don't have. All right. I hope it's not too, sort of all over the place, but bear with me today. Okay, but we begin on number 1. Can we go to Bryce?
In this section, we introduce the all-important first functions. These functions will allow us to solve equations. 3 days, lesson plan. Take our time and make sure everyone.
Okay, so let's give this a shot. Yeah, and so in terms of the schedule, I mean, like we saw, we have 3 days on the inverse trig, but I have only 2 homework assignments in here and only 2 learning objectives and only 2 of everything. So we're really going to take our time, and especially because we're changing the game plan pretty dramatically. But we have time to kind of do this the right way. We do have a quiz coming up on Monday. I guarantee you we will get through the stuff in here that you need to know in order to do the quiz stuff that's on this section, okay? All right, so let's give it a shot. So the first thing we're going to do is something you do not have. So I'm going to ask you guys to solve this equation. Cosine of theta equals 1/2 for theta between 0 and 360 degrees. Yeah, we're going to find theta. So first, you guys are going to have to remind me to slow down and make sure you have time to copy, because I am very not used to you guys having to copy problems because they're normally typed up for you. So when you're ready, let's see if we can grab that unit circle from the first page of the packet. Oh, by the way, on the quiz, you are going to have another resource you can bring with you. Let me see if we can find it. Not that one. Yeah, this one. You guys can bring this page 37 into the quiz if you wish. Okay. Also the unit circle. Yeah, unit circle for the rest of the semester, but on this quiz you can bring this reference sheet. All right, so let's go to the unit circle. And we're looking for places where the cosine is equal to a half. Again, is the cosine the x or the y? Is the x. So we look for angles where the x coordinate is a half and see if you guys can find any. Anybody find an angle where the x coordinate is a half? 60 degrees. So there's my half, and it happens at the 60-degree line. So one solution to that equation I gave you is theta equals 60 degrees. Good? Okay. Are there any other solutions? Any other angles where the x is a half? It's just barely on the screen, but there is another place down here, I'll keep it in blue, where the x is a half. And that's at 300 degrees. There's the other answer. So that equation has two different answers. Theta is 60 degrees, theta is 300 degrees. Good? I don't know what that button is yet, but we will in a few minutes. Okay. Yeah, so we'll get there. All right, so that's that. Now suppose that we want the same question, but instead of saying I want all the answers from 0 to 360, suppose that I say I want all the answers from 0 to 2 pi. Can you look at this and do very little more work to find me all the solutions between 0 and 2 pi? What's the first solution? It's pi over 3. What's the second solution? 5 pi over 3. So let me come back to the page that we were on, which I think is this guy. So we'll write down our answers here. Okay, so then the solutions from the unit circle were 60 and 300. And then if we want to solve it on the radian version of things, then we end up with theta is pi over 3 and 5 pi over 3. And I want to kind of, relate this to the graphs. We've been talking a lot about graphs. If I were interested, I have to slow down. I have to just remind me, Ian, we're still copying. So if I want to think about finding solutions graphically to the equation cosine theta is a half, what should I graph? I should graph cosine of theta. Can you guys point? Does the cosine of theta start at the top, the middle, or the bottom? Can you point to one of those things? Cosine of theta starts at the top. Where does sine of theta start? In the middle. Okay, so we're graphing cosine of theta. There it is. Cosine of theta is that one. I'll do the degree version of things here. So that ends at 360. And what else should I graph if I'm thinking about solving that equation at the top? I should graph what, the x-axis? Yeah, we want to graph y equals 1/2, right? We just graphed y equals cosine theta. We're going to graph y equals a half. With your arm, what does y equals a half look like? Horizontal line. So we're going to put a horizontal line at a half. How do I know where a half is? Well, how much is this number at the top on the cosine? Is 1. Okay, now I know where a half is. So there's y equals a half. And do you see the solutions to the equation in that picture? How do you find them in the picture? You're intersecting. So we're looking for places where these two things hit each other. How many intersection points do you see? You see 2. There's one there. Second one there. I don't know what they are just by looking at the picture, but at least I can confidently say there's going to be 2 of these guys. But we do know what they are because we did the work already. What's the first one? Is it 60? I'll do degrees here. And the second one was at 300. And do those numbers make sense just in terms of the scale and the degrees? Sure. Right, that 60 is a little under the first x-intercept, which is at 90. And the last one is pretty close to 360, 300, so it's reasonable. Any questions on that? Okay, suppose that I'm getting a tiny bit ahead of the audible that I'm calling, another audible. Suppose that I made it cosine of theta equals not 0.5, but equals 0.4. What would happen to my green line? Just shift it down a little bit. How many answers would you expect? 2. What if instead of 0.5, it was at 0.9? Shift it up. How many answers would you expect? 2. What if it was at negative 0.3? 2. You're starting to see the trend here. Whatever line you draw here, you're going to find 2 points of intersection. Okay, that is a slight lie. There's some extremes that just behave differently from the others. If you draw a line at y equals -1, how many times will it hit the cosine graph? Just the once. -1 is, what's that? Yeah, it's kind of related to this thing Garrett had mentioned a while back about the multiplicity. Like it does feel like there's 2 of them down there because it's quite flat. But we would just write theta equals 180 and that would be a single answer. It would just look different. There is one other extreme and that's at the top, right? I mean, like it hits the top once here at the beginning. Whether or not we include the 360, it depends on what the question asks. But I just want to point out that any number you pick, you're going to find 2 solutions, unless you happen to be one at the really special extremes, the -1 and the +1. Suppose I said cosine of theta equals 5. Where is that line? It's way up here. How many solutions does that equation have? 0. Okay, so any number you pick between -1 and 1, 2 solutions. Pick -1 or 1, they're special. You might only have 1 solution. Anything bigger than 1 or smaller than -1, no solutions at all. Okay, now suppose that we add to that question, solve cosine of theta equals 1/2. Topher. You're right. This guy does have 2 solutions here. The reason I still want to say that 1 is special, like -1 is special. If I'm thinking of the graph of sine, and I'm drawing up there at 1, how many solutions does it have? Just the 1. And cosine, sorry, and at -1, how many solutions does it have? Just 1. So like, you're right. I mean, it is included. It's only kind of artificially included here because I really went a little bit too far on the far right. Like I should go from 0 and then stop just before I get to 360. If I, like 0 and 360 are kind of the same. So you're right. There are 2 of them to this problem, but 1 is special, just like -1 is special. It just needs to be thought about a little bit more. That's all. Okay, what's the difference? It's the same question, right? How many solutions does that equation have? I didn't put the constraints on theta. How many solutions does that have? It has infinitely many. Because if I were to just have not been so lazy and stopped my cosine graph, I could have gone another period for cosine and I would have found another 2 answers, right? And if I go left, I'd find more answers over there. I'll have infinitely many answers. Okay, we have time to write that down. Let's solve. We know that we have one answer that we found before. Let's just do degrees for right now. How much was the first theta we found? It was 60 degrees. How much was the other theta we found? 300. Those were our 2, I'm going to call them the basic answers, or the fundamental answers. So we'll say something like, from before. We know those 2 answers. Here's the question. If you are currently sitting on 60 degrees, how far do you have to go to get to the next answer? at 240? From 300, how far do you have to go to the next answer? You have to go 120. So you go 240 one way and 120 the other way. It's kind of weird. I don't really like that we're going different amounts. How about we just treat them like the different creatures that they are? How about I just look at 60 and I ignore the bottom one? If I want to get back to 60, how far do I have to go starting at 60 and then making my way back to the 60? I have to go 360 from there. All right, so that lands me at 420. Suppose you're at 420, which looks an awful lot like 60. How far do you have to go from 420 to get back to 60? Another 360. This is a pattern I can buy into. If you are at an angle and you want to get back to that same angle, you just keep adding 360s. And then a separate statement, if you are focusing only on the 300 and you start at 300, how far do you have to go to get back to the next 300? It's 360. And then we don't have to worry about this kind of asymmetry that we just found. So that's what we're going to do. We're going to really treat these two fundamental solutions as being two different kinds of creatures. We're here. What happened? Anybody see how did we just go back to the beginning? Oh, I hit undo. Okay, so it just brought me back to the last page I had written something on. Okay. All right, so then if I want the complete picture, if you are sitting at 60 degrees, how much do you have to add to land back on the 60 degrees again? You have to add 360. Couldn't you add a lot of 360s? You could add several, like 7 360s or 8 360s. So we're going to call it K. You can call it any letter you want. But 360 times any integer. And if you are currently at the other fundamental solution, that 300, how much do you have to add to get to the things like it? 360K. It will be fancy, actually, instead of using the dittos. Mathematicians don't like to write a lot of stuff, so we invent symbols, which means you have to memorize them so that you can write less stuff. I don't need you to memorize them, but anybody know the fancy symbol for the set of all integers? It doesn't look like a fish. That's a reasonable guess. There's symbols that look like fish. So for some reason, the symbol that we use for integers is a z with a little fancy extra line drawn in the side. Anybody know German? No? The German word for number is Zahlen. I think this is why we use z. And to say that it's an element of a set, maybe you guys have seen that Greek letter, meaning it's an element of a set. So instead of writing k as an integer, you could just write that. It means the same thing. Of course, it took us 60 seconds to talk about what those symbols are, but anyway. Yes, integer. You just read it like it's in English, like on the top.
That extra line on the C, is that being sloppy or is that
That extra line at the top right or the actual diagonal? The diagonal line is part of the symbol. Yes, it's like a fancy Z. You guys have seen the set for all real numbers, haven't you? Haven't you guys seen that one? Yeah, it's the same kind of idea. An R with an extra line, Z with an extra line. All right, so we've got that. Can you guys do this? So maybe I should have specified theta in degrees is what we just did. But can you guys, with your neighbors, try solving our favorite equation, cosine theta equals half, where theta is in radians. So talk to your neighbors and try to write down the solutions, all infinitely many of them, to that equation. Okay, can we come back together? Again, we start with our fundamental solutions. We knew them from before. We got pi over 3 and we got 5 pi over 3. And then instead of adding 360s, what are we adding in radian mode? We're adding 2 pi's. So you add a bunch of 2 pi's. How many of them? Some arbitrary number of them. That way we get all of them. Notice that k is allowed to be negative. Negative k's are finding us the solutions to the left. We want to include all of them. Questions on that? Okay, next question. I wonder if I keep hitting extend page, like if you actually look at the PDF, what will it do? Will it be like so tiny because it's trying to fit it on an 8.5 by 11? I don't know. Go to another page. Okay, with your neighbors, can you solve this equation? Sine of theta equals negative root 2 over 2, theta in degrees. Okay, so almost every group has a 225 and a 315 for the fundamental angles. And then again, we want all of them unless it specifies only tell me the ones between here and here. You got to give me this plus 360k, plus 360k, k an integer. One group had a different answer. I'm going to cross this one off. What did you guys say? Theta equals negative 45 plus 360k. Is that all right? Sure, because negative 45 lands on the same place as 315. If you subtract 360k's, then you would say, let's go, same thing. Yeah, makes no difference. So again, lots and lots of different possible right answers. For me, I'm always going to give you the two answers that are between 0 and 360, but you could pick from any one of the infinitely many answers that, and just call it a fundamental answer. Would this be okay? Suppose that I cross off this guy and I said, okay, my other fundamental answer is going to be 585 degrees. Where is 585? What is 585 really? It's really 225, right? Okay, so is this good? I have my two solutions. Yeah. What can you say about the two solutions that are not crossed off? They're the same set of angles. I have two things written, but I don't have I don't have all the angles. At no point will I land on 315 if I write this. So it's fine to pick from the infinitely many things, but you got to make sure you're really picking two different fundamental things.
So 585 plus 660 wouldn't work because it doesn't include the 225.
Yeah, but k could be negative, so the negatives are built in there. Yeah. Right. Okay. So then, I really thought I could just undo some of the stuff that I had written. Okay. All right. So that's good, or the one that's crossed off. Both fine. All right. Let's kind of answer one of these special ones here. Can you guys solve sine of theta equals 1? Theta in radians. Remember, the ones and the negative ones are special. So can we find a fundamental solution? Pi over 2 works, right? That gets us to the top of the circle. And if we're putting pi over 2, then what are we adding at the end? 2 pi times k. Bet you guys are happy we have the shortcut symbols now, right? I mean, you're not going to have like a million of these on a test, so you're not going to have to write them a million times, but this is a separate problem, so it deserves its own little special symbols. How about another fundamental solution? There isn't one. This is the special one. Right? If you're up at the top of the circle, only hit it once. If you're at the bottom of the circle, only hit it once. So that's a complete solution set. Questions on that? All right. Next question. Can you guys estimate the solutions to cosine of theta equals 0.45 between 0 and 360? No calculators. You can either look at the unit circle or you can look at a rough sketch of the cosine function. But just see if you can ballpark some solutions between 0 and 360. No calculators. Okay, so let's think about this. So I've got my my graph, my very rough graph of cosine up here, and I picked 0.45 to relate it to this 0.5 that we know very well from today. And we know the solutions here are 60 and 300 degrees. And now I'm going to draw it at 0.45. Are we going above or below the purple? Below. I'll exaggerate just so I can kind of squeeze it in, but it's not very far below. Or I could just move the whole thing. If we put it below, so this is at y equals 0.45, we find two other solutions. And these solutions here shouldn't be very far from 60 and 300. Is this first solution more or less than 60? Is it more than 60? It might be tempting because we brought the 0.5 down a little bit. Maybe you bring the 60 down a little bit. But if you look at the picture, it's not. I mean, we get a little bit bigger. So, all right, so if you want to say like 63 degrees or 68 degrees, something a little bit bigger than 60. How about the 300? That one's a little bit less. We're a little left of the 300 here. So maybe you say like 295. It will be symmetric. So these guys don't agree with each other. Allie, what would you change this to if I like 63? Maybe 297, right? If I'm saying it's 3 degrees off, then there's nice symmetry that we're definitely going to take advantage of in the coming classes. Okay, that's using the graph. But I'd also like you to be able to use that unit circle and come up with the same conclusion here. Okay, so we've already seen the x-coordinate is half right here. So this is at 0.5, 60 degrees. We've seen that. So if I'm doing 0.45, where is x equal to 0.45? Left or right of this left? And it's kind of weird because you think you're moving left, you think you're getting smaller. Well, you are on the x-axis, but if you are forced to go find an angle on the circle, then it has gotten a tiny bit bigger than the 60-degree angle you were at before. Buy that? So either look at the circle or look at the graph. For me, I'm a graph person, but whatever is more natural for you, you should do. Okay, now, to say about 57, or about 63 or about 297 is fine for an estimate, but we'd sure like a way to come up with a more accurate estimate than this. Finally, what's the main topic for today and the next few classes? Is the inverse trig functions. And so this is where the inverse trig functions come in. So here's what we do. You guys know that the opposite of multiplication is division. I'm going to start saying inverse instead of saying opposite. The inverse of multiplication is division. The inverse of subtraction, addition. The inverse of squaring something, square rooting the thing. You have lots of practice with lots of different kinds of inverses. Here is a new kind of inverse. The inverse of taking the cosine of something is called the inverse cosine. And the symbol for the inverse cosine is cosine to the -1. Just like there is a symbol radical, which means take the square root, here is the symbol which undoes the cosine. So here's what I'd like to do with this symbol. First of all, let's go back to our standard equation. Cosine of theta is 0.5. That was our basic one that we know everything about. And what I'd like to do is pretend that we couldn't just look at the unit circle and grab the answers. Pretend that we weren't able to do that because we're about to not be able to do it for 0.45. So suppose we can't do it. What I need to do is somehow get my hands on theta. Theta is currently buried inside of the cosine. The way to undo cosine is this thing called inverse cosine. It is very bad to say, okay, I'm going to divide both sides by cosine, and I'll have my answer. That is not how you undo cosine, because this is not cosine times theta. That is a function. Cosine does something very, very strange to an angle. So don't do that. What you do instead, I'm going to write that equation again with a little bit more space. Same equation. But what I'm going to do to the left-hand side is take the inverse cosine of it. Just like, what would you do to solve this equation? You would take the square root of both sides. We are going to take the inverse cosine of both sides. Inverse cosine of this thing, that's how we write it, just like you would write that square root symbol. And whatever you do to the one side, you must do to the other. And the way the inverse cosine is defined, what happens when you have inverse cosine of theta? It's just theta, and that's the point. So we're going to write theta equals inverse cosine of 0.5.
All the other inverses we've ever really dealt with are, they might be complicated, but they're things you can sort of do on paper.
Mm-hmm.
Is the inverse cosine like that, or is it just drawing like a huge table of values?
I think it's like the estimating that you guys just did with the, I mean, you did an inverse cosine by estimating 63 degrees. So however you can do it. If you have a table of values, great. We're going to use the calculator. It's basically got a table of values inside of it.
Yeah,
It's not doing something, no. I mean, there are, how did they come up with tables of values, hundreds of years ago? There are like algebraic processes, I think, I can't tell you what they are, where just like you could estimate square roots by doing some stuff, I think you could estimate this by doing some stuff. I don't know what those algorithms are. But at some point, they must have had some technique for doing something. At the moment, we're just going to hit a button. Okay, one thing I want to say. It is going to be completely okay to not write that step. If you see cosine of theta equals 0.5, you can then immediately just move the cosine over and make it an inverse cosine. Again, cosine on one side becomes inverse cosine in the other. That's what we just said. Until you are very comfortable with inverse cosine, and some of you maybe already are, I would encourage you to write that step in the middle. You are doing something to both sides. You are taking the inverse cosine, and then you're taking advantage of the fact that it cancels with the cosine. I'd encourage you to write that for a while. Okay, so how do we find this thing? Well, got a button on the calculator. So finally, we'll get to Garrett's question. So on the calculator, we're going to find the inverse cosine of 0.5. You will see the symbol in yellow right above the cosine. That's convenient. So you hit second, cosine, 0.5. Good question. What mode are we in? Remember I had said before you hit sine, cosine, or tangent, think about the mode. I'm still saying the same thing. We've been doing degrees for a while. Let's be in degree mode at the moment. So go into mode and make sure you're in degrees. What was our fundamental answer? Our first one for this cosine theta is a half. It was 60 degrees, wasn't it? Okay, so you hit enter. Calculator says 60 degrees. Garrett, what was your question from way back when? What was the other answer besides 60? It's 300. Would you guys like for the calculator to sometimes tell you that the inverse cosine of 0.5 is 60, and then other times tell you that the inverse cosine is 300? That doesn't sound good to me. I want the calculator to be internally consistent, not just with itself, but with every other calculator and computer in the world. I want everybody's electronic device in the world to tell me the same answer. We're making a choice here. The people programming the calculator have made a choice to never tell you 300. You can hit enter as many times as you want. It will keep telling you 60, which means we need to think about the geometry. We need to think about the picture. If you know one answer is 60, and you believe the symmetry that's going on here, how much is the end of my first cycle? It is 360, 2 pi. So if I know that I'm going 60 degrees in that way to get to the first solution, I'm sure buying that I'm going 60 degrees in from the end of this thing. So if you know 60, you can find 300. And that's what we're going to have to do, because all of a sudden in a minute, the answers aren't going to be as nice as 60 and 300 sitting on our unit circle.
I still see why
The inverse cosine is, we are defining it to be a function. which means one input better have one output. That's the issue. Yeah. All right, so we've got that. It says that the inverse cosine of 0.5 is 60 degrees. We then need to do some thinking and analyzing to get the other answer. The other fundamental answer is 300. All right, suppose that we just take a step back to some of the other nice ones before we get to the ugly one, the 0.45. Can we, where are we going here? Where was our second nice one? Can we do this one? Can you guys write that equation right there? Sine of theta is negative radical 2 over 2. Can you write down something with inverse? Don't just go to the calculator. I'd really like you to get some practice with the writing that inverse sine stuff. So do something to both sides, practice writing it, and then when you're ready, type something on the calculator. Okay, what are we trying to find the inverse sine of? Negative root 2 over 2. Type it in very carefully. Inverse sine negative square root of 2 over 2. Was I careful enough? I was not. But it's so easy to do because you didn't put the parentheses in there. So why should you have to close them? But you need to know that they're there. Okay. What was our fund? We had two fundamental answers. Do you guys remember what the two fundamental answers were? That's right. Every table except for one said 225 and 315. We know the calculator is about to make a choice. It can't give us both answers and still be a function. Which one does it pick? Picks neither one. 5 tables got it wrong. Good job, guys. You picked the right answer. Okay, 315 is fine. It's the same as negative 45. But the calculator is making a choice. And at this moment, it seems like it's kind of an arbitrary choice because I've been saying 0 to 360 is how I'm always going to write it. All of a sudden, the calculator throws this curveball at us. As long as you know what to expect, then the calculator's behavior is very predictable. So let's start talking about what to expect. Another audible. One other thing before we leave this. Suppose that I change to degree mode. What is I'm sorry, I said degree mode. I meant radian mode. Just changed to radian mode. What's the radian version of 45 degrees? It's pi over 4. The calculator will never tell me pi over 4. The calculator can give me a decimal. If I do second entry, I'm asking it for the inverse sine of the same exact thing. I'm expecting it to say negative 45 degrees, but it's not going to, right? Because I just told it I want something in radians, not degrees. It's really disconcerting to see those two lines back to back. On the one hand, inverse sine of negative root 2 over 2 is negative 45. On the other hand, it's negative 0.785. But you guys know we haven't typed in the same thing. It looks the same. But on the one hand, negative 45 is a degree answer. On the other hand, 0.785 is a radian answer. If I were to compare with pi over 4, can you guys do that in your head? You guys can. How much is pi over 4 in your head, but also looking at the stuff on the board? It's 0.785. You got some massive calculating ability up there. It's telling me pi over 4. It's telling me the radian answer, but it'll never say anything with pi. So it's really important. If you hit any of those 3 buttons, including to get to the yellow things right above, you know what mode you're in, because the calculator is not going to give you any indication.
So is it sometimes better to solve them in degree and then convert the degree into radian?
It's completely up to you and what the problem is asking you for. Part of the goal of this course, an important part, I think, is to gain comfort with radians. So I'm going to encourage folks to try to enter their zone of discomfort and stop going to degrees automatically. But you can answer any question we talk about this semester.
Like both of the times you did that, one of them gave you an exact answer and the other one was an approximate answer.
Right.
So would you want to go with the exact answer?
Good question. Most of the things that we're typing in are not going to be like root 2 over 2, which is perfectly one of our nice answers. So if we were to do inverse sine of negative 0.4, that's the radian version. That's the degree version. Neither of them is a nice number. So like it's going to be pretty rare. And if it's a nice number in the first place, then you probably should have just grabbed it off the unit circle anyway. Yeah, good question. Chris.
Well, if you're doing the one for the radian,
Okay, so, all right, so Chris has a nice way to kind of find if there's pi's hidden in a number that it's not obvious. So, oops, sorry. If we're back in radian mode and it tells us the answer and we don't know that that's pi over 4, if you divide by pi and it is something nice, then you will ferret out the nice number. 0.25, that's a 1/4. That's nice. Can somebody grab the thinker? Just pass it. I don't feel like getting it. Just grab it. Good job. Okay. Suppose that we come back to the question that we have not answered yet, which was the 0.45 one. Yeah. Okay, so we are again solving cosine of theta is 0.45. We've estimated 63 degrees and 297. Those are my estimates. You could have different estimates. Let's see if you guys can find both answers between 0 and 360. Now you're allowed to use your calculator. Cosine of theta is 0.45. Find both answers between 0 and 360. Okay, so at this point, we're taking the inverse cosine of 0.45. The calculator is only allowed to give you one answer. What answer does it give you? 63 let's say about 63.3. Is that all right? Okay, so that's the first answer. Our estimate was pretty good. And if we want the other answer, the calculator is of no help at all. We need to think about the symmetry. We need to recognize that if 63 is an answer, then 360 minus that number is the other answer. So 360 minus the 63.3. And so that is around 296.7. You could also do negative 63.3. But the directions said you got to give me the two numbers between 0 and 360. Yeah. Kate. It's a good question. We're going to get into that a little bit more next time. But I'll say for cosine, suppose that I just make up the answer to some problem. I'll tell you that the answer to some problem is 100 degrees, meaning I've found some point right here that is a winner for me. So if that's the one answer, can you guys see where the other answer is going to be? If I just keep drawing this line over, we found our other answer is up there. Do you believe it's still 360 minus? If it's 100 in this way, sure seems like it's 100 in that way. For cosine, yes, 360 minus. Whether we're positive, negative, doesn't matter. Yeah. All right, so what I want to do now, what do I want to do now? Okay, so that one's good and fine. What if I asked you for the two radian answers? Can you guys solve that same equation? We're still up here. I would like the two answers between 0 and 2 pi. Calculator active. So if you find the first answer is about 1.1, we used to be subtracting from 360. What do we do to find the other answer now? Subtract from 2 pi. And then we type into the calculator 5.3, 5.2. Okay. Any questions on that? All right, next thing. I now need to tell you what decision the programmers who wrote the programming stuff for your calculator have made. So I will tell you. We'll finally go back to something that's in the packet. Can you guys jump to page 40? And we're going to jump down here to number 8 in the middle. And I've got this second column that says inverse cosine. And so I want to tell you what the inputs are and what the outputs are. All right, first of all, the inputs. Inverse cosine. Let's take a step back. Cosine. What do you stick, what kind of a thing do you put inside of the cosine function? You stick an angle in there, right? Cosine takes in an angle and it spits out some number. So if we go to inverse cosine, then the input is going to be that number that got spat out. And what's the output going to be? An angle. And every time we hit the inverse cosine button, it says, here's the angle. So the output is going to be some angle, and I will tell you where that lives. Let's think about the input. What's the biggest number that cosine might spit out? 1. It's the highest number you'll ever get for the cosine. What's the lowest number? -1. So the input for the inverse cosine is the output for the cosine. You plug in any number you want between -1 and 1, and the inverse cosine can deal with it. So over here, if we ask it for the inverse cosine of 0.45, no problems. If we ask it for the inverse cosine of 0.99, no problem. If we ask it for the inverse cosine of 1, no problem. If we ask it for the inverse cosine of 1.00001, problem. Yeah, they should update it so it says fail. That's more current, right? I want to be current. Domain error. Yeah, the domain is -1 to 1. Don't bother trying to put something in there that doesn't exist. Let's think about the output now. This is the part where there was a choice that was made. The output for the cosine function, and I'll talk a little bit more about why this was a natural choice, is the inverse cosine will always give you an angle between 0 degrees and 180 degrees, or if you prefer radians, 0 to pi. If you hit the inverse cosine button and you hit enter, you will always get some number between 0 and 180. You will never get something negative. You will never get 181. It will always be between 0 and 180. That was not for the inverse cosine. That was for the inverse sine, which has a different set of outputs. So down here at the bottom, the inverse sine function, the input, how high does sine normally get? 1. How low? -1. Same inputs. You can only plug in a number between -1 and 1. Different outputs. If you hit the inverse sine button on your calculator, you will always get an angle between -90 degrees and 90 degrees. Or -pi/2 to pi/2. At the moment, these choices, it's okay for them to seem arbitrary. It's also okay to put them on your index card for the quiz so that you know what answers to expect. This is going to be a non-calculator quiz. I'm not going to ask you for inverse cosine of 0.45. I'm going to ask you for inverse cosine of things that are on the unit circle. Okay? Does it make sense that we got -45 as an answer instead of 315? Yes, calculator is programmed to never tell you 315. It will find the thing between -90 and 90. Okay, next page, inverse tangent. Just think about the tangent function. How high does the tangent function get? Infinity. How low? -infinity. You could put any number you want to into the inverse tangent function. You will never get that error that we saw before. The output is going to look very familiar to one of those guys, -90 to 90. Does that make it like cosine or sine? Makes it like sine with one small change, 2 small changes. What's the difference between that and the sine answer? For sine, the answer could be 90. For tangent, you will never get the answer to be 90. You could get 89.999, but you'll never get it to say exactly 90. And again, if you're a radian person, then it's here. But, you know, you're on like different Facebook groups and stuff. So. Okay, so the last few questions I want to talk about today. But was this like too all over the place today? Was this okay? It's going into the packet. I guarantee it is. But I'm hoping it wasn't too, yeah, okay. Well, the good news is that I had planned on 3 days for what we only have 2 days of stuff in the packet. So I think we'll be okay in terms of timing. So I do have just a couple more quick questions I'm going to ask you to do in the last 2 minutes. But I will say in terms of the homework, I am not officially assigning this thing until Monday night. You'll be able to do a bunch of it. There will be some questions that won't look familiar yet. You can decide to however much of it you want to do. Don't hand anything in on Monday, okay? All right, but there is a quiz on Monday on some of the stuff that we've talked about today. Okay, so the last few things I would like for you guys to do is with your unit circle, find the values of these 5 things. And can I ask, are you going to get 2 answers again like we did before? The inverse cosine of radical 2 over 2 is a single number. It's a function. It is a single number. There are going to be 2 choices for you on the unit circle. Which one do you pick? You got to look at how inverse cosine is defined. You're going to pick the one that's between 0 and 180. There will only be one between 0 and 180. All right, so we'll put that back, try these 5, and then we'll call it a day.